The Nesio Bridge is located in Amsterdam, Netherlands, and was opened in 2006. It spans the Amsterdam-Rhine Canal, providing a much quicker pedestrian and cycle link between the city of Amsterdam and a new suburb, Eiburg, which is constructed on land recently reclaimed from the sea. The Nesio Bridge is a single cable suspension bridge with a total length of 780 metres. It is curved in plan and bifurcates at each end to split the pedestrian and cyclist approaches. The 170-metre long main span of the bridge is made of steel and has a clearance of 10 metres to allow for the shipping traffic on the canal below. Due to this, the cyclist approach ramps are very long and the pedestrian access is provided by 2 spiral staircases. The approach spans and foundations are made from reinforced concrete. The Nesio Bridge won the 2007 Structural Award, a prestigious international award recognising structural excellence, as well as 2 other national prizes.
The Nesio Bridge encourages cycling, which is a popular and environmentally friendly mode of transport, and it has been seamlessly incorporated into the local cycle network. The dividing of the pedestrian and cycle paths is a key safety feature, and another is the 180-degree bend at the top of each staircase, stopping cyclists. The proportions of the bridge appear reasonable due to the ratio between the height of the masts and the length of the span between them, signalling an efficient span-sag ratio. The projection of the mast gives the bridge a sense of importance and makes it an iconic structure along the canal. The south side approach loops around a newly created wetland habitat consisting of winding ponds and reed beds that can be viewed from the bridge. The integration of this habitat helps sustain the local biodiversity, including plants and animal species. Wetlands also serve as a sustainable method of urban drainage. The gentle changes in plan and elevation creates flowing shapes, and the hanger cables do not appear to cross each other, creating good order within the structure. However, this order is somewhat broken where the steel and concrete sections of the bridge meet, and the 2 different columns are placed close together. The mast and deck are coated in a white paint. The combination of the colour white and the angled sides of the deck give the illusion of a narrower overall section, enhancing its slenderness. The imposed loads from pedestrians and cyclists on a bridge are much lighter than that on vehicular bridges, therefore the bridge can be designed as a more lightweight structure. The slender design of the Nesio Bridge has been achieved using high-strength and low-density materials that transfer loads efficiently through the structure.
Due to the loading conditions, a suspension bridge was an ideal choice for the Nesio Bridge. The bridge has 2 large masts that support the single cable, which carries the deck via a series of hangers cables. The hangers transfer the load from the deck to the main cable, which is in tension, meaning that it feels like it is being stretched. The deck, cables, and masts are all primary structure elements, as they are all required to support the bridge. Some of the vertical force is transferred to the foundation via the mast, while the remaining vertical and horizontal components transferred by the anchoring of the cables. In a conventional suspension bridge, this anchor is into the ground, but because the soil conditions on the side are poor, the Nesio Bridge is self-anchored. This means the main cable is anchored to the deck itself, which carries the horizontal component of the force from the cable. Maximum bending in the deck occurs at midspan. Therefore, at this location, the deck must have the highest stiffness. This is achieved by using a deep triangular steel girder section. In other locations where a lower stiffness is required, a more rectangular box section is used, such as where it meets the concrete approach spans. The shape and the depth of the deck cross-section changes frequently along its length to adjust to the required stiffness. This ensures efficient use of materials, which is a key aspect in sustainable design, and reduces the amount of embodied carbon. The sloping sides of the box section make it streamlined, therefore reduces the area wind loading can act on, thus lessening large wind loads. The asymmetrical triangular section takes this into account, but was also designed in order to minimize the interruption to the random navigation of the ships below. The bridge deck also splits in 2 at both ends, which improves the lateral stiffness of the structure, meaning how well the bridge resists bending sideways due to an applied load. The bridge is supported by piled foundations due to the soft soil on site. The steel columns at both ends experience wind loading, which causes horizontal vibrations and therefore have to be stiff. Due to this, there is a reinforced concrete box acting as a pile cap, providing additional electric stiffness in order to prevent moments being transferred into the piles and thereby prevent overturning. The reinforced concrete box also prevents twisting moment.
Steel was chosen as the primary structural material for the main span of the bridge, as it is a high strength and durable material, which is a suitable choice for the 120-year design life of a bridge. All the exposed steel components are painted in order to reduce the corrosion and thereby increase their durability. However, this requires regular maintenance. The cables are coated in zinc to provide durability and corrosion resistance. The use of steel also allows for large parts of the bridge to be prefabricated off-site and assembled quickly on-site. In contrast, the approach spans made from concrete are cast in situ, meaning concrete is poured into formwork on-site, which is more time-consuming. Concrete cannot efficiently span as far as steel, but the use of regular spaced columns means the depth of the concrete approaches can be similar to that of the main steel box section. The choice of using different materials for the two parts of the bridge means that they are both used efficiently and is a good example of sustainable design.
These are the primary connections details for the net seal bridge. This is a steel plate connections that provides additional lateral stiffness at the fabrication point. This is the connection between deck and the column. It's a more complex junction that ensures the tension in the cable. This is the junction connecting the mast and the main cable. A paint joint was chosen as this allows the cable to rotate. This is the connection between the main cable and the hanger cables. They are all paint connections. The force from the main cable on each mast is countered by an opposing force from two backstays, providing stability. The bifurcation of two backstays combined with curved plan, which allows one-sided cable supports to shift sets along the length, provide lateral stability. Furthermore, the shape of the deck cross-section resists the torsional effects as well as limiting sway due to horizontal loading. In addition, tuned mass dampers and visco dampers are provided in the deck at quarter span and mid-span respectively to reduce the oscillation of the bridge. Tuned mass damper is a device to reduce vibration by adding a mass on a spring. Visco damper is a hydraulic device that can dissipate the kinetic energy. Long-span lightweight bridges are susceptible to uncomfortable oscillations caused by wind. The most reliable way to predict the response of a bridge to wind loading is to build a scale model and test it in a wind tunnel under the predicted wind conditions. It is important that the form and the strength are modeled correctly to obtain an accurate output. The wind tunnel testing of net seal bridge indicates that the mid-span vibration amplitude at 10 meters per second wind would be 60 millimeters. This is an acceptable displacement for a pedestrian bridge. Normally, a suspension bridge is constructed by first erecting the mast and the cables. Then the deck is built in sections. Because the net seal bridge is self-anchored, the deck has to be constructed first in order to anchor the cable. The Amsterdam-Rhine Canal is an important shipping route, and it could therefore only be closed for 12 hours for the construction of the bridge. As a result of this, the whole main span of the deck was assembled in Rotterdam and transported in by the canal. The whole 187-meter-long element was then lifted onto temporary stays by two floating cranes. The temporary stays was anchored into finalized foundations.
This construction method was a sustainable solution as the steel box girder was prefabricated locally, resulting in reduced carbon emissions associated with transportation. The use of finalized foundations as a temporary anchor also saved a large amount of materials. This and the increased speed of construction due to prefabricating the deck reduced the overall carbon emissions associated with the construction process. Lifting in the steel section in one piece meant that the rest of the construction process could be undertaken without interrupting the traffic on the canal.
We observed that the junction between the steel deck and concrete deck has two columns positioned closely together, and this interrupts the order of the columns. A possible alternative is to relocate the concrete column further back and hence change the concrete deck to a propped cantilever. This would lead to a more uniform spacing between columns.
The depth of the steel deck is likely over-designed purely for the construction sequence, as the deck was supported from fewer points until it was connected to the main cable. If more temporary supports were allowed to be positioned in the canal for a short period, this may have allowed a mid-span depth of less than 1.9 metres, making the bridge look more slender.
As the bridge greatly reduces the travel time between Amsterdam and Eiberg, a number of mopeds have been observed using the pedestrian and cyclist path, causing annoyance to users and potentially dangerous situations. A potential prevention method is to install signs to warn mopeds to dismount and occasional traffic controls to discourage mopeds from using the bridge.
Overall, we think the National Bridge creates a pleasant crossing for pedestrians and cyclists that serves its function, but it's also aesthetically pleasing. Its gentle curves and few numbers of elements means it is simple yet elegant. The bridge has many refinements that emphasize the good detailing of the bridge. The bridge is also a positive contribution to a sustainable built environment due to its efficient design and the facilitation of sustainable transport and biodiversity.